Today we'll be discussing mass spectrometry. Mass spectrometry can be used on elements and compounds, and the following useful information can be found about these samples. For elements, we can determine the percent abundance of individual isotopes. For example, we know that chlorine has two isotopes, chlorine 35 and chlorine 37. With mass spectrometry, we can work out the percent abundance of these two isotopes of chlorine. For compounds, we can also determine the molar mass of the entire molecule, as well as some information about the structure of the compound. Take ethanol as an example. So we know ethanol has two carbon, and then there is the functional group hydroxyl group attached towards the end. We can use mass spectrometry to obtain some useful information about the structure. As molecules, they will undergo fragmentation in the process. So we'll discuss that shortly. But first, let me put down some uses of mass spectrometry when it comes to studying samples of elements and compounds. So for elements, we can find the relative abundance or the percent abundance of individual isotopes. And for compounds, we can determine the molar mass of the molecule, as well as deducing the structure of the molecule. So next, we'll turn to the setup of mass spectrometry, okay, and that is the mass spectrometer itself. So we'll look at the different components of a mass spectrometer to see how it works. So there are 5 different parts of a basic mass spectrometer, starting with vaporization chamber. So it looks kind of like this. You see the mass spectrometer. There are actually 2 different types of mass spectrometer. One is based on the an electromagnet, and the other is what we call a time of flight mass spectrometer. So in DSC, we'll be looking at a deflection type mass spectrometer. So this is the deflection type mass spectrometer. So the different parts of the mass spectrometer are, number 1, the vaporization chamber, which as the name suggests, it vaporizes the sample. And then we have the ionization chamber, which ionizes the sample into positively charged ions. And then we have the deflection chamber. Actually, before that, we have the acceleration chamber. So it accelerates ion to high kinetic energy. Then we have the deflection chamber, which uses an electromagnet to bend the ions around. So therefore the term deflection. Finally, we have the last stage, detection. So the ions, they are directed to the detector, okay, which is located at this end. So when they hit the detector, they will be, detected. Okay, so we'll look at what happens in each of these stages here, starting with vaporization. So in the vaporization stage, all samples will be turned into gas. So if X is the sample, so it can have any state. It can be solid, it can be liquid, it can be gas. So in vaporization stage, it will be turned into a gas. Then in the ionization stage, we will use an electron gun to knock electron out of the sample, okay, be it an element or a compound, to form positively charged ion out of it. So the equation is X gas plus a slow moving electron from the electron gun, a fast moving electron from the electron gun. So this is a fast moving electron. Yeah, it will knock out electrons from the sample to form a positively charged ion, and in this process 2 electrons will be knocked out. Okay, so these are slow moving. So you can think of it like this: if this is X, the original sample, with just 1 proton and maybe 1 electron in orbit, then by knocking out that electron in orbit with a very fast moving electron, so you see this is that fast moving electron from the electron gun, you will then be able to get a positively charged ion as well as 2 slow moving electrons in the process. So this is why the overall end result is that you have 1 electron removed from the neutral sample. So the neutral sample can be an atom or molecule, but the result is that you get a positively charged ion. It is possible to form a positive 2 charged ion, though it is highly unlikely, because once an ion becomes positively charged, additional electrons will be lost with difficulty. So positively charged ion, additionally, so you can have, so let me put it down this way. So +1 charged ions and +2 charged ions, can both be formed, even though the latter is less likely. So can both be formed. And below are the equations, okay, for describing their formation. So overall, the formation of +1 charged ion can be summarized by this equation. So X gas becomes X plus gas and an electron. So you see this equation is different from the one we wrote before, because this is after simplifying the starting equation here. So we had 1 electron on the left, 2 electrons on the right. So if we subtract 1 electrons from both sides, we have a net result of losing 1 electrons on the right. So this is the simplified equation of the one we just wrote. The formation of a +1 charged ion can be described by this equation. Once the +1 charged ion is formed, we can use the electron gun to knock out additional electrons to form an X2 plus charged ion. So in this process, another electron will be knocked out. So why is the +2 charged ion less likely to form? That's because it's derived from an already positively charged ion. So it's harder for this ion to lose electrons, as they will attract. The electrons and the positive ion, they will attract, as one is positive, one is negative. So +2 charged ions are harder to form. So they are harder to form because the X plus ion will attract electron more strongly than in the case of +1 charged ion. So you can see that in here, in +1 charged ion, this is neutral. So a neutral gaseous atom will attract electron less strongly. Okay, so they do not attract each other as strongly. So therefore, +1 charged ion, they can be formed more readily. So that's what you need to know about ionization. Then we have acceleration. So the point of forming positive ions is that we can then accelerate the positive charged ion with an electric field. Okay, so acceleration is done by an electric field. So which in this case is just a negatively charged plate. So electric field. Remember, we produce some positive charged ion in the ionization step. Okay, so these positive charged ion can then be accelerated towards a negatively charged plate. So we have the positive ions here. As they move near the negative charged plate, they will move more quickly. Okay, they will be accelerated. Okay, so you will see this happening. So after they move past the negative charged plate, they will gain speed. So they go from slow moving to fast moving. So this is the before and below shows what happens after the acceleration step. Okay, so you have before and after. Okay, after the acceleration step, okay, the ions will enter the deflection zone. So in the deflection zone, deflection is done by a magnetic field instead, okay, as opposed to the electric field we use in acceleration. So this is stage 4. We have deflection. So in deflection, this is done by a magnetic field. And this magnetic field is set up by an electromagnet that we can adjust the strength of. So magnetic field. So the deflection of the ion is based on what we call the mass to charge ratio. So the extent of deflection, how much the ions are deflected, that's the extent of deflection, is dependent on the inverse of the mass to charge ratio. In other words, the bigger the charge of the ion and the smaller the mass of the ion, the greater the extent of deflection. Okay, or you can also write it this way: is inversely proportional to mass to charge ratio. Okay, inversely proportional to mass to charge ratio. And what does mass to charge ratio mean, and how do we calculate it? So mass to charge ratio, sometimes you will see it written as m/e. In this case, I'm writing it as m/z. So you can write either depending on your liking. So you have mass to charge ratio. So m stands for mass, z stands for charge. So we can find this value by dividing the mass of the ion by the charge of the ion. So note that the terms here, they appear in a different order, okay, than in the extent of deflection. That's because the extent of deflection is inversely proportional to mass to charge, okay, not directly proportional. So take 2 ions as an example. If we have 35Cl plus, and when we have CH3CH2OH plus, how do we calculate the mass to charge ratio of these 2 ions? Okay, so to calculate the mass, we just add up all the atomic masses, okay, like you normally would when you find the molar mass of a substance. So this is found by dividing 35 by +1. So you have the mass up top, and then you have the charge at the bottom. So the answer would be 35, okay, for 35Cl plus, the mass to charge ratio. And what about the mass to charge ratio of this other ion in here? Well, we need to look up the periodic table. So we have a total of 2 carbon here, so 12 times 2, 6 hydrogen in total, so 1 times 6, and then we have an additional oxygen, so 16. So they are divided by +1, which is the charge of this ion, you see. So we need to add up everything in the formula in here, and then divide it by the charge. And like I mentioned earlier, sometimes the charge can be 2 plus charge. So the denominator will sometimes be written as +2. Okay, so for example, in here, what is the answer? So 16 plus 24 plus 6 would be 46. Yeah, and like I said, ions can sometimes be +2 charge. So if we do an additional round of ionization on 35 chlorine plus, the mass to charge ratio will then become 35 divided by +2, which would then give 17.5. So just pay attention to the charge and the mass, and you should do just fine. This is how we find the mass to charge ratio. So the bigger the mass to charge ratio, the smaller the deflection, okay? And so different samples, they will be deflected differently in the mass spectrometer. So say, for example, this is the mass spectrometer again. We are feeding in 2 samples into the mass spectrometer. Let's say I have a smaller 35Cl plus form in the ionization stage, and then another 37Cl plus forming the ionization stage. So they are formed from the sample 35Cl and 37Cl, let's just say. Yeah, and then they are subjected to the same magnetic field strength. Okay, so here they are entering the deflection stage. So this is the deflection stage by the electromagnet, by the magnetic field. Okay, so this is an electromagnet put in place. We use electromagnet instead of permanent magnet because we want to adjust the size of the magnetic field so that we can direct ions of different mass to charge ratio to the detector. So the detector is here, but these ions originally they are accelerated by the, you see, electric field in this direction. So they both want to move forward in this direction. But thanks to the electromagnet and because of some interaction between magnetic field and ions, as the ions they move into the deflection zone, they will bend around. Okay, so they will bend around the corner, and then they will be moving towards the detector instead. But because these ions they have different mass to charge ratio, the extent to which they will be deflected will be different. So if you look at these two ions, you can find that the one on top has a mass to charge ratio of 35, and this has a mass to charge ratio of 37. And recall what we just saw in here, that the extent of deflection is inversely proportional to mass to charge ratio. You should be able to predict that chlorine 35 plus, okay, it will be deflected more. So chlorine 35 plus, they may take a path that will lead right to the detector, but chlorine 37, it is deflected by a lesser extent, and so it might hit the wall of the mass spectrometer. And anything that hit the wall of the mass spectrometer, they will be lost. Okay, these signals will be lost. And anything hitting the detector, so remember this is where the detector is, these will be picked up, okay, these signals. So we say 35 Cl plus is detected here. And then we can repeat the experiment, okay, because we have only collected data for 35 chlorine plus. We haven't yet collected any data for 37 Cl plus, as they have hit the wall, and then the you can assume that those samples are lost. So we will now have to make the electromagnet stronger. We increase the strength of the electromagnet so that the magnet is now more powerful than before. So with a more powerful magnet, the 35 and 37 Cl plus, they continue to be ionized to become 35 Cl plus and 37 Cl plus. And as usual, the 35 Cl plus will be deflected more than the 37 Cl plus due to the difference in mass to charge ratio. But because this time the electromagnet is stronger, the 35 Cl plus, okay, it will be deflected so much that it hit the left wall, and that the 37 Cl plus is deflected by just the right amount onto the detector. And so you see every time one particular sample with a certain mass to charge ratio will be detected, while all the other samples with a different mass to charge ratio, they will be lost, as they will either hit the left wall, you see like in here, like what happens to 35 Cl plus, so it's lost. So all the 35 Cl plus are lost. And in here, all the 37 Cl plus are lost. So at any given time, only one type of ion with a certain mass to charge ratio, they will be able to hit the detector and then be detected. So this is the workings, okay, of a mass spectrometer. And by measuring the amount of samples that hit the detector when we use a weaker electromagnet in here and a stronger electromagnet on the right, we can have all the ions coming from different isotopes hitting the detector at the end. So you have stronger electromagnet here. So from that, we can create what we call a mass spectrum. So the mass spectrum for elements and compounds, they will be different. So the mass spectrum of elements will show the percent abundance of different isotopes. So this will show, so take the chlorine example we saw earlier. So take chlorine as an example. Like we said, it has two different isotopes, chlorine 35 and chlorine 37. So in the vaporization step, they will both be turned into gaseous atoms, and then in the ionization stage, they will both be turned into positively charged ion. So let's not worry about the 2 plus charged ion in this case. Yeah, so this is what happens in vaporization, where the samples are turned into gas. And this is what happens in the ionization step, where the samples are then ionized to form positive charged ion. Then these ions, they will be deflected differently by the magnetic field, and by adjusting the strength of the magnetic field, they hit the detector at a different time, okay, when a different electromagnetic strength is used. But eventually we'll have some information about the abundance of chlorine-35 and chlorine-37. And we found that there are more samples hitting the detector, okay, for 35Cl+, and there are less samples, okay, fewer samples hitting the detector which come from the 37Cl+ ion. So with this information, we can then draw the mass spectrum. So this is the mass spectrum of chlorine, showing only the ions coming from the atoms. So we'll have a longer stick here representing 35Cl+, and a shorter stick here representing 37Cl+. So the y-axis shows the percent abundance. So you see the red line is taller than the blue line. Actually, it should, let me draw it to scale. It should be 3 times as tall. Okay, so 3 times as tall, because the percentage here is 75%, and for chlorine-37, it is only 25%. Okay, in the percent abundance. That's the mass spectrum of just the elements. So with different elements, we'll have a different mass spectrum. So remember this graph, we call it mass spectrum. And the x-axis is usually the mass to charge ratio. So instead of seeing these actual species in here, you will just be seeing their mass to charge ratio, which are of course 35 and 37. Yeah, because the mass to charge ratio is divided by the mass, dividing the mass by the charge. So it's 37 divided by +1 and 35 divided by +1 respectively. So you have these values in here. So with other elements, okay, the mass spectrum will look different. Take bromine as another example. So take bromine as another example. So bromine, like chlorine, has also 2 isotopes, 79 and 81 Br. And just like chlorine, it will undergo vaporization and ionization like before, yeah, where it turns into a gas and later a positively charged ion. But this time the percent abundance are different. Okay, they are roughly 50%. Okay, or more precisely, it should be 51% and 49%. But it's close enough to a 1-to-1 ratio. So you have close to 1-to-1 ratio, whereas for chlorine you have close to a 3-to-1 ratio. So this is why this red line is 3 times as tall as the blue line. So on the right, the graph for bromine should look like this. So you have mass to charge ratio as the x-axis again, the percent abundance as the y-axis. So you will have a red line and a blue line here that are just as tall. Okay, so this is 49% abundant, and the 79 Br is 51% abundant. So their mass to charge ratio are respectively 79 and 81, because the first graph, the first line in red correspond to 79 Br plus, and the second line, the blue line, corresponds to 81 Br plus. So the mass to charge ratio will be 79 divided by +1 and 81 divided by +1 respectively. So you get these numbers. Okay, so you have 81. Right, like in here. So from the mass spectrum, we can obtain some information about the relative abundance of isotopes, okay, of the same element. So you see chlorine is an element, but it doesn't just have 1 isotope, it has 2 isotopes, chlorine-35 and chlorine-37. Bromine is another element which has another two isotopes, 79Br and 81Br. So by studying these samples with the mass spectrometer, we can find out how abundant the different isotopes are, okay, in an element. So let me shrink this down and I paste this in here. So we can then use mass spectrometer or mass spectrometry to study compounds. Okay, the kind of information we obtain from compounds are different. So what you saw on the left is about elements. So this is about element. So we will now be turning our attention to compounds. Okay, so mass spectrum of compounds. So the events that like a compound would experience in a mass spectrometer is similar to an element. They are also vaporization, ionization, acceleration, deflection, and detection. But unlike in an element, okay, the compound will also undergo fragmentation. Actually, with element, they will also undergo fragmentation, but I have simplified the picture here as what you see in here. So starting with just 35Cl atom and 37Cl atom. In fact, we should start from 35Cl, 35Cl, or 35Cl, 37Cl, or 37Cl, 37Cl, as chlorine should normally be a diatomic element. But yeah, let's not worry about that, okay? And we will go back to the mass spectrum of compounds. So with a compound like ethanol, so you know ethanol has the formula CH3, CH2, C11OH. So this is ethanol. So let's just condense it into a molecular formula. So C3H, 2, 3, 4, 5, 6, H6O. So this is a propanol. Sorry, this is propanol with 3 carbons here. So when we put this sample into the mass spectrometer, so note that this is a compound now. What we were studying earlier are elements. Okay, so this is an element, bromine is an element. So here we are dealing with a compound. So this compound would undergo vaporization and it will turn into a gas. Okay, so let me just copy the structure real quick here first. So you have the compound propanol. The propanol will then be ionized into, what will be vaporized into propanol gas. And then the propanol gas will then undergo ionization to form a positively charged ion of propanol, okay, which has just 1 electron stripped away from the entire molecule. So we have, you can say C3H6O gas, yeah, in this part, and then we have C3H6O plus. So the entire thing is a positively charged ion, or you can just write the plus charge on the outside. So but note that the plus charge applies to the entire molecule. So we call this a molecular ion. So this molecular ion is formed when electrons are knocked out from this neutral molecule. So we have actually stripped away an electron like we did in here. So we are actually stripping electron away from this neutral sample in order to, form these positive charge ions on the right. And in here, when we strip away 1 electron from this neutral molecule, so this is our gaseous molecule. It is turned into gaseous state because of the vaporization stage. So remember, all samples fed into the mass spectrometer, they will first undergo vaporization. So they turn from whatever state they are in to a gaseous state molecule. And then they will undergo ionization so that they become molecular ion. But unlike in the elements in here, the molecular ion, it will undergo additional round of fragmentation. Okay, it will break into pieces, okay, this molecular ion. So this is due to the excess kinetic energy that comes from the electron gun in the ionization process. Remember, we shoot electrons on our gaseous molecule to form these molecular ions. So sometimes there's too much kinetic energy in the molecular ion, and that will cause the molecular ion to fragmentize, to undergo fragmentation, that is. and it will usually break along the weaker bonds in the molecule, the weak points in the molecule. For example, the molecule may break here, yeah, and this will form two fragments. So you have a CH3 and a CH2CHO fragment. Note that it is a positive ion splitting up into fragments. So one of the daughter fragment will be positive charge, while the other will be neutral. Yeah. Alternatively, the molecular ion may split up at this CC bond, and it will form other fragments. So let's take a look at what kind of fragments we'll get, okay, with the molecular ion here. If the molecular ion split up in here, compared to when it splits up at this position, so what kind of fragments may form, okay? So here we are looking at something new, yeah, never discussed before in this lesson. So we call this the fragmentation of molecular ion. So this is the positive charge ion we were dealing with just now. So of the molecular ion, so it will then form CH3 plus and CH2CHO. So this part here is the CH3, okay, part. And this part right here, let me use another line, okay, just a straight line here, to describe the CH2CHO. Because a positively charged ion is splitting up into two different fragments, yeah, one of these fragments will be positive charged, but it's a random event, okay? So it's either the left fragment that get a positive charge, or the right fragment that get a positive charge, okay? And then they would be detected, okay? They would be detected. Alternatively, the molecular ion can also break up at this position, yeah, rather than at this position. And so other fragments may form. In this case, maybe you can guess, okay? So take a moment to guess what kind of fragments will form. So it is actually C2H5 and CHO. Yeah, and just like before, it's a chance event, okay, that either of these fragments will get the positive charge. So it could be that the C2H5 fragment gets the positive charge, and that the CHO will be left with a neutral charge, or I should just say it is neutral, the CHO. Or it can be that the C2H5 fragment is neutral, and that the CHO fragment is then positively charged. So, and because any of these fragmentation pattern is possible, so in the mass spectrometry, in the actual mass spectrometry, all the positive charge fragments, they will be detected. So all these fragments, they should be detected. And because they each have a different mass to charge ratio, they will then produce 4 different peaks, okay, on our mass spectrum. So let me put this down in here. Only positively charged fragments, okay, and the molecular ion. So, and the molecular ion will be detected in the mass spectrometer, because ionization and deflection, you see in the deflection stage, only ions can be deflected. Yeah, so if you produce something uncharged in mass spectrometer, they will just head straight to the wall here. There will be no effect, okay, on the ions. The electromagnet will have no effect on those neutral samples. So they will just head straight to the wall and they will be lost. Only when you have positive charge ions will those ions be deflected successfully and then head straight to the detector instead. So any uncharged fragments, they will just be heading straight to the wall and those signals will be lost. So this is why I said only positively charged fragments and molecular ion will be detected, okay, in the mass spectrometer. So this includes also the molecular ion we have in here. And because all these have different mass to charge ratio, so let's take a look at the mass to charge ratio of the molecular ion here. So this is 12 times 2 as there are 3 carbon, 1 times 6 as there are 6 hydrogen, plus 16 divided by the charge, which is plus 1. So you have, remember, this is the mass, so the entire mass, and this is the charge. Okay, so the charge. So we divide the mass by the charge, and then we'll have, so what's the answer? I think it's 58. So 36, 42, yeah, 58. And then each of these fragments, they will have different mass to charge ratio. So let me put this in here. you have this fragment in here, and then you have this fragment in here, and then you have another fragment in here, and finally this fragment is also possible. They can be formed in the fragmentation process. You can individually calculate the mass to charge ratio. So this one will have mass to charge ratio of 15. This will have mass to charge ratio of 43. So make sure you stop the video to check that you really get those masses. Okay. The third one will have mass to charge ratio of 29, and the fourth one will have also mass to charge ratio of 29. So they will all appear on your mass spectrum of the molecule. So, and just like before, we have you see the mass spectrum, but this time this is the mass spectrum of propanol. So earlier this is the mass spectrum of chlorine, right? So of chlorine, and this is the mass spectrum of bromine. So we have mass spectrum of chlorine, we have mass spectrum of bromine, and this is the mass spectrum of propanol. So C3H6O, propanol. And unlike in the mass spectrum of chlorine and bromine, you have many peaks in here. First, you will have this molecular ion peak, which usually is the peak with the highest mass to charge ratio, as this comes from the molecule. Okay, so this peak is the molecular ion peak, we say. And because this molecular ion, we said it undergoes fragmentation to form many different fragments. So these are called the fragments. Yeah, these fragments, they must have smaller mass to charge ratio than the molecular ion, as they come from the molecular ion. So they will be found to the left of this molecular ion peak. So let me label the peaks for you. This is the molecular ion peak due to the entire molecular ion. So you have CH3, CH2, C double bond OH. Yeah, so this peak is due to the entire molecular ion. And when these molecular ion undergo fragmentation, so it will form additional peaks, okay, like these ones you see. So it may form a CH3 peak, CH3 plus peak, okay, so that it has a mass to charge ratio of 15. So 15 you see here. It will produce like peaks with mass to charge ratio of 29. So this could be like a CH3 plus fragment. So this could be a CH3CH2 plus fragment or a CHO plus fragment, yeah, which has a mass of 29. So yeah, you can see that we can split up this molecular ion to form a CH3 plus. So CH3 plus, yeah, or I can have C2H5 plus. So C2H5 plus, or I can have a CHO plus. So this is CHO plus ion, okay, which come from this part of the molecule. And finally, we can also have a CH2 CHO plus. So they have CH2 CHO plus. So CH2 CHO plus. So this will be another positive fragment that we can get. So you have a peak of 49 in here. So in this case, the height of the peak doesn't really matter. Yeah, it is the value of the mass to charge ratio that matters. So basically, if you see a mass, so this should be 43, my bad. So if you see a difference of peak, okay, so difference in mass to charge ratio of 15, so this corresponds to the loss of a CH3 group. Okay, yeah, because if you lose a fragment that has a mass of 15, okay, yeah, that would most likely be a CH3 fragment. Yeah, and if you have lost a mass of 29 units of mass, you see when you compute the difference here, 58 minus 43 is 15. But when you compare these two peaks, 58 minus 29 will be 29. Okay, so when you see a loss of 29 units of mass, this could be due to the loss of a larger fragment than the one with a 15 units of mass. So this is CH3CH2, for example. Yeah, so by comparing the different peaks in here, we can tell what kind of compound this is. Okay, so even though it doesn't tell you the exact structure of the molecule, you can tell that, well, if so let me try to explain it this way. So you have CH3, CH2, C double bond OH. So this is the molecular ion. Yeah, if it undergoes fragmentation at this position and it strip away the CH3 group, the resultant fragment, so this is the resultant fragment, it will have 15 units of mass, like smaller, okay, than the parent molecule. Yeah, and if it break up at this position and forms this fragment, yeah, so then there will be 29 units of mass to charge ratio smaller than the parent fragment. So by comparing these peaks, okay, we can tell the structure of this molecule. Okay, so let me just label it on here. So, right, so if this part is lost, okay, so if this part is lost, the resultant fragment will have a mass to charge ratio of, so you see this is CH2CHO, right? So this corresponds to this fragment. But if instead the molecule break up at this CC bond, you see, yeah, then the resultant fragment, CHO plus, so you see this is CHO plus, it will have a mass to charge ratio of 29. Yeah, so this is how you get this fragment peak at this position and at this position. Yeah, so a certain molecule will have a unique mass spectrum, okay, and we can use it to identify like isomers, okay. So if we have two isomers, we can tell which is which, okay, by studying the mass spectrum. So for example, in here, when we look at the mass spectrum of C3H6O isomers. So remember that isomers, they are molecules with the same molecular formula but a different structural formula. So we have 1, 2, 3. So this is propanol. So propanol, it's CH3CH2CHO. So you have CH3CH2CHO. And then we have propanone. So this is propanone. So C double bond O, C. So the H's, they are put on the side. If you count the total number of carbon, hydrogen, and oxygen in both of these compounds, you'll find that they both have the same molecular formula, C3H6O. So CH3COCH3. This is called propanol on top, as it has the aldehyde functional group, so anal because of the CHO group. And then we have anone because of the CO double bond. So this we call it propanone. Okay, so anone is due to the CO double bond, okay, the carbonyl group. And they are isomers, which means when they undergo the vaporization and ionization, as you remember, they will form a positive charge ions. So they will form positive charge ion. So first they will undergo vaporization in the mass spectrometer. Then they will undergo ionization to become a positive charge ion of each type. So with propanol, you just have to add a positive charge on the outside, you see. So let me copy this for use later. So you have a positive charge molecular ion, yeah, coming from propanol, yeah, which you will just write as CH3COCH3 plus. And from propanol, you will have the same thing happening, okay, you will have CH3CH2CHO plus. Yeah, note that in ionization, you knock out electrons, so you form positive charge ion. So this is CH3CH2CHO plus, like that. And just like we discussed before, these ions, okay, the molecular ion, they will undergo fragmentation differently. So with CH3CH2CHO plus, maybe let me draw a box around here first before you become confused. So these two are known as molecular ions. as they are derived from the molecule, okay, our sample molecule on the left. So this is the sample molecule. Then the molecular ion will undergo, remember, fragmentation. Okay, so fragmentation. So fragmentation can happen along the weaker bonds on the molecule, usually at the CC bonds. So you see these CC bonds in here. They are usually where the molecule will break. Yeah, it's unlikely to break at the stronger bonds like double bonds or CH bonds. Okay, CH bonds are stronger than CC bond. So therefore, as you can imagine, these fragments may occur. So there are two different positions where this molecule on top can break. It may break here, because this is where the first CC bond is, or it may break here. So if it breaks at the first position, you should be able to get that, like there will be these two possible fragments formed. So you'll either have CH3 or CH2C double bond OH, yeah, formed. Okay, so these are the two fragments that you get when you split up the CC bond at this position. And like we discussed before, either of these fragments can get the positive charge. So it says either the positive fragment, the left-hand side fragment getting the positive charge, or the right-hand side fragment getting the positive charge. Okay, so let me just write it this way. You will have CH3 and CH2CHO, or CH3 and CH2CHO. So in the first case, you'll have the left fragment getting the plus charge. In the second case, you have the right fragment getting the plus charge. Okay, so it's a chance event which fragment getting the positive charge. So you have, this is the first fragment, and this will be your second fragment here. So these two will be the second fragment. And remember, only the positive charge fragment will be detected. So therefore, this will be detected, this will be detected. Yeah, and in the second, like a molecule below, okay, molecular ion below, we can break up the molecule at another CC bond, and this time it will result in another two fragments, you see. So it will form a C2. So you see this is the C2H5 fragment and another CHO fragment. And just like we discussed, either the left fragment or the right fragment can get a positive charge. So it may be the left fragment C2H5 getting a positive charge. It may be the right fragment CHO getting a positive charge. So yeah, but at the end, because there are many samples, okay, you put into the mass spectrometer, so you can expect that all these fragments will form. Okay, there's a statistical chance that all these fragments will form and therefore be detected. So you'll have the CHO and a C2H5 and then the CHO fragment on the right. So this is the CHO fragment. So, and let's summarize what we see so far. We have C2H5 plus fragment, we have CHO plus fragment. So what are their mass to charge ratio? So the mass to charge ratio would be 15, and this will be, make sure you stop the video to actually calculate the mass to charge ratio. So the mass to charge ratio of this molecular ion here would be, because it's C3H6O, so it should be 12 times 3 plus 1 times 6 plus 16, which is, so 15 plus 6. So you have so you have 36 plus 6 plus 16. So it should be 58. So the mass to charge ratio of both of these molecular ions should be 58, as they are isomers. So isomers should share the same, like molar mass, and therefore the same mass to charge ratio. The fragments here, however, they will have different mass to charge ratio. This will be 43, this will be 29, and this also will be 29. So that means at the end, when you look at the mass spectrum of the top molecule, propanol, this is what it should look like. So you'll have the molecular ion fragment, 58, and then you will have these fragments. So this is the molecular ion 58, and then you will have those fragments on the right found to the left of this peak. Okay, so you'll have one at 15, one at 29. I note that it's not drawn to scale. Okay, so you have the molecular ion peak. So this is the molecular ion peak, and these will be the fragments peak. Okay, yeah, this that came from here. Okay, so all these, they will just come over here. Yeah, maybe I'll draw the arrow later. Okay, so you can see these are the fragment peaks, and this one on the right will be the molecular ion peak. Yeah, so this one. So you have one at 58, and then you have some at 15, 29, 43. Don't mind the height of these peaks, okay? Because the height really doesn't matter. It is the pattern that you see in here. How many peaks you see that help distinguish between isomers. You'll see. So let's look at the propanone next. So propanone has 2 CC bonds, okay, at which the molecule can undergo fragmentation. So it can undergo fragmentation at either this position or this position. But as you see, because this is a symmetric molecule, so it means whether it break up at this position or at this position, it really wouldn't make a difference, okay? The fragments will just be the same. So they both will produce the same fragment, which is CH3, this part, and then the other part, CH3CO. Okay, so you'll have CH3CO. So this part would also be CH3CO, you see, because the molecule is symmetric. Yeah, so and just like before, it can either have the first fragment getting the plus charge or the second fragment getting the plus charge. So that means you will have 2 peaks detected with mass to charge ratio of respectively 15 and 43. So when we look at the mass spectrum of propanone this time, so this is propanone, we will continue to have a molecular ion peak which has a mass to charge ratio of 58 because this came from this guy. Yeah, and then we will have, so this is the molecular ion peak, we will have other fragment peaks. Okay, so you see from here, so these are the fragment peaks and these are the fragment peaks for the other molecule here. So the mass spectrum you see on the left is for propanol. Propanol will produce these 1, 2, 3, 4 peaks. And for propanone will only produce how many peaks? You should see only 3 peaks. 2 fragment peaks, one is 15, one is 43, and then the molecular ion peak at 58. So this is why I said the height really doesn't matter. Okay, the height of the peaks really doesn't matter, because you really just need to look at this, the number of peaks. Okay, and that should help you know which isomer we are talking about here. So even though these 2 molecules, they are isomer with the same molecular ion peak, okay, 58 at 58, they should produce a different fragment pattern. And from this different fragmentation pattern, we can identify which mass spectrum, okay, belongs to which molecule. Okay, so let me just summarize what we saw in here on top right hand corner. So different isomers have different structure, of course. Okay, so different isomers have different structure. This means they would form different fragments during fragmentation. So this means because of the difference in structure, the 2 isomers will form different fragments, okay, in fragmentation. However, yeah, so you have different fragment peaks in here. So the purple ones we just saw, okay, these purple peaks, these are the fragments, okay, so they will have different fragment ions. However, it must be noted that they, however, will have the same mass to charge ratio for the molecular ion peak. Because they are isomers, that means the molecules, okay, in the unfragmentized state will have the same number of atoms, total number of atoms. So it should not be a surprise that they have the same mass to charge ratio in this molecular ion state. So they have the same mass to charge ratio for the molecular ion. So you have the same peak for molecular ion. And finally, point number 4, from the number of peaks, so from the number of peaks, we can distinguish between the isomers because they will produce a different number of peaks. So distinguish between the two isomers, propanol and propanol. So in our example, propanol, you see produces 1 peak, 2 peak, 3 peak, 4 peaks. It produces 4 peaks. And propanol on the right, it produces only 3 peaks. So it's kind of like a barcode, okay, for a molecule. A different molecule will produce a different, fragmentation pattern, and as a result, a different number of peaks. So that's how we know. So you have 4 peaks in here for propanol, while for propanol, it has only 3 peaks. So these are kind of like, the barcode of the molecule. So this is how we use mass spectrometer.